All right, so here we go with talking about some solids. This won't be a super long video for this one. I just want to make sure I cover a couple things that show up in the textbook, and so we have a couple terms that we are familiar with and that we have seen. So there's two types of solids that we're going to talk about. They tend to fall into, or solids tend to fall into two categories. They're crystalline, that have an orderly repeating arrangement of atoms, and amorphous, that lack an orderly repeating pattern. As an example, I always like to show silicon dioxide and the amorphous and crystalline form, because these are things that you will probably be familiar with, in that this is quartz, which is the crystalline form of silicon dioxide, and this is glass, which is the amorphous form of silicon dioxide. And so as you can see, right, the quartz over here on the left, that has an orderly repeating pattern. All of the bonds are the same length. They're all like making this nice hexagonal shape. Whereas glass on the right, it has the same connectivity mostly, right? But there are some sections that are not in a hexagonal pattern, and then some, right, that are kind of twisted. It is not orderly or repeating, right? And so that would be amorphous. But they both have the same fundamental formula. So now within each of these categories, right, crystalline and amorphous, there are four types of solids. That's a metallic solid, where metals are held together, or metal atoms are held together by metallic bonds. Some examples of these would be copper and iron. Ionic solids, where anions and cations, right, metals and nonmetals, are held together by an electrostatic interaction, or ionic bonds, sodium chloride, calcium carbonate, those kind of things. There are covalent network solids, where the atoms are held together by covalent bonds. Examples are diamond and graphite. We'll see pictures of those a little while later here. And then, of course, molecular solids. Molecules are held together by intermolecular forces, things like ice or paraffin wax. And then within solids, the way we talk about the structure of solids, there are two main parts to those structures. Those would be a unit cell, or the smallest repeating group of atoms in a crystalline solid, and then the crystal lattice, which is a system of three-dimensional geometries that help to define the structure of a crystalline solid. So here's a little thing about the attractive force that holds together a lot of crystalline solids. All right, it is Coulomb's law, and basically that electrostatic force is equal to a constant times the charges divided by the distance between the particles squared, right? So as the charge increases, the force increases, but also as the distance decreases, the charge is going to increase, right? So the closer the particles are, the stronger the force, the larger the charge on the particles, also the stronger the force. So some pictures. These are the geometric patterns that help to define a crystal lattice, right? We have our cubic, our tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, and triclinic. All right, and remember that these are all in 3 dimensions, and so even though things like monoclinic, tetragonal, and orthorhombic, even triclinic look the same, right? If you notice the angles that are defined there, they are not the same. Same with the length of the sides, if you notice the A, B, and C there. So you can pause, check these out. I'm going to move on to the next. So here are some basic units, the way that atoms in solids are stacked. There's simple cubic, right, where you have atoms at the corners of a cube. There is body-centered, where you have them at the corners, and then one in the middle of that cube, or body-centered. And then you've got face-centered, where you have atoms at the corners of a cube, but then also along the faces, right? And these simple cubic, body-centered, and face-centered work with any of those geometries that were in the previous picture. And then here, as promised, is for some covalent network solids, the difference between diamond structure and graphite structure. So the big difference here being that this has a three-dimensional structure, right, where you have every carbon atom having a tetrahedral structure there, whereas here you have graphite and it is a 2D structure where you have all these carbons that are covalently bonded, but then you also have these forces, intermolecular forces, right, that exist between the sheets of graphite, which is why diamond is really strong while graphite slides across itself. It makes good pencil lead, it makes a good lubricant, things like that. So the last thing that we'll talk here about in solids is alloys, right? And that is, if you remember, a mixture of two or more metals. There are two types of alloys that you will come across. Those are interstitial, which those are when the metal atoms fit between other atoms of a larger metal. And then there's substitutional, where metal atoms replace other metal atoms in the alloy. And to help you out with this, I have a picture here of the pure metal, right, not an alloy. Then interstitial, where atoms are fitting between the larger ones. The substitutional, where other atoms are replacing some of the ones. And then you have a substitutional interstitial alloy, where you have some in the middle and some that are replacing them. Examples of each are written here. And so that's about it for solids. We're not going to get into too much specifics here. So yeah, that's it. And I will see you in class.